You ask a computer to write a poem or navigate a car through city traffic, and it responds with what feels like human intuition. But if we peel back the interface, we find a system that doesn't actually understand words or see the road. To a computer, the entire world, from a text prompt to a video feed, is processed as a massive string of numbers. These numbers act like precise coordinates on a giant, multi-dimensional map. The AI takes your input, converts them into these numeric coordinates, and runs them through an equation. The goal is to calculate which specific word has the highest mathematical probability of coming next. Ultimately, every thought an AI has is the result of a massive, highly tuned equation predicting the next step in a sequence. This creates a challenge for the people building these systems. If AI is just an equation, how does a human programmer write the math required to compose a sonnet or identify a stop sign? The complexity is too high for any person to manually code. Instead of writing the rules themselves, programmers feed the computer trillions of data points, like the entire text of Wikipedia, and let the machine build its own internal rules for how those numbers relate to each other. This process of a computer refining its own internal math based on massive amounts of data is what we call training. To see how this works, we start with a simple goal: predicting the price of a house based on its square footage. This chart shows our examples. Each dot represents a real house, with size on the bottom and price up the side. To start, the AI makes a random guess, drawing a straight line across the graph. At first, it's nowhere near the actual data points. This line is defined by two values, its steepness and its starting position. In the industry, these numbers are called weights. They are the internal dials the AI can turn to change the line's shape. By adjusting these weights, the AI can tilt or shift the line. Its objective is to move the line until it cuts perfectly through the middle of all those data points. To fix the line, the AI needs a way to measure how wrong its current guess is. Since a machine can't see the graph, it calculates its failure mathematically. It calculates the distance between its incorrect line and every single actual house price on the chart. When you add all those distances together, you get a single number representing the total error. We call this the loss function. The goal of training is simple: turn the dials, the weights, until that loss function is as close to zero as possible. The AI adjusts its weights automatically, using a method that doesn't require a human to tell it which way to move. Imagine the loss function as a 3D landscape. Peaks are huge errors, valleys are the smallest. The AI is a dot on a steep slope. Like a blindfolded climber, it feels for the steepest downward direction and takes a step. This is gradient descent. The size of that step is the learning rate. If the step is too big, the AI might leap right over the valley. If it's too small, it will take forever to reach the bottom. Step by step, it follows the mathematical gravity of the slope. When it hits the bottom of the valley, it has found the perfect weights to fit the data. Predicting a house price is straightforward because a house only has a few coordinates, like its size or age. But a sentence like write a poem has thousands of individual coordinates based on how those words have been used in billions of other sentences. To handle this, AI uses neural networks, a massive digital web where every connection acts like one of those dials or weights we saw earlier. The math used to manage these giant tables of numbers is called linear algebra. Instead of adjusting two weights on a flat graph, a modern AI might adjust trillions of them at once. It's the same process of moving downhill toward a lower error, just performed on a scale that's nearly impossible for a human to visualize. By navigating this trillion-dimensional landscape, the machine finds the specific arrangement of weights that allows it to predict the next word in a poem as accurately as it predicted the price of a house. Even after all that work, an AI trained only on raw internet data might give responses that are technically accurate but unhelpful or rude, simply because it's mimicking everything it found online. To fix this, engineers use alignment. They give the AI a prompt, and if it gives a lame or bad response, they manually show it what a good response looks like. Mathematically, this shifts the target y-coordinate on the map, forcing the model to run gradient descent again to nudge its weights toward that more helpful destination. These are the 4 unglamorous steps that power the industry: collecting data, making a guess with weights, measuring the error, and stepping downhill to find a better solution. Every amazing thing you see an AI do is the result of billions of tiny mathematical adjustments, slowly finding their way home.